Good morning everyone, Dr. Nat here. So we are going to continue on our lecture 4 or chapter 4, which is on cache memory, and this is going to be part number 2. So briefly, I have told you that we have 3 types of mapping function for the cache, which is the first one is direct mapping, and then we have fully associative mapping. Sometimes we call it associative, but to distinguish it from the third mapping, we call it fully associative, and the third one is called set associative. So let's talk about the direct mapping. So this figure shows you direct mapping. So we have M blocks over here. This is block number 1. Sorry, this is block 0, block 1. So you would have, let me zoom this in. So you would have block 0, block 1, block 2, etc. And each block will be mapped onto one line. Each block will be mapped onto one line. So the total number of blocks would be M, capital M, and the total number of lines in the cache memory would be small m. So again, I would like to remind you that capital M is so much greater than small m. So you don't have enough cache lines. This is why we need the mapping. So if this is direct mapping whereby one block is assigned to one line, where do the rest of the blocks go, right? Because capital M is obviously bigger than small m. So here you can see that we have a system going on here. So the first M blocks would be mapped this way. So block 0 is assigned to cache line 0. Block number 1 is assigned to cache line number 1. Block number 2 is going to be assigned at cache line number 2. And let's say you have 100 cache line. So this would be cache line number 99, right? So M would be 100, let's say. Okay, so this is cache line 99, and this would be block 99 as well. And where does block 100 go? Block 100 would go over here. And then you would have 101. Then you have 100, and then you would have 2M minus 1, which is 2M is 200 minus 1. It is 199. So this repeats on until all the memory blocks are assigned to a line. So it's almost like round robin scheme, right? Alright, so here the line number of cache to which a particular block can map is given by cache line is equal to main memory block address modulo number of lines in cache. Modulo means that you divide it, and this is going to be the remainder. Division, divide, and remainder. How do I explain this? Let me try to explain this. If you are not familiar with modulo, let me try to explain this in the simplest way possible. So let's say you have, remember that we have 100 cache lines. Therefore, our maximum cache line number is going to be 99. And then the main memory block address, let's say we have around 300. So let's write that here. M is going to be 300. And your small m is going to be 100. Okay? So your cache line is going to be going from 0 to 99. And your block memory will go from 0 to 299. These are your block numbers. These are your cache lines. Okay, and this is block numbers. Okay, so let's say I want to map block, let's say block number 32. Okay, so block, let me write that nicely. Let's use a different color. So block 32, I want to know where I should map it. So, but this is straightforward, right? Because our cache line is actually 99, goes up until 0 to 99. So a block 32 would be mapped exactly at, block 32 would be mapped to cache line 32. So what if we have block 132, where would this be mapped to? So here I've written the equation. So we are looking for the cache line number over here, and this is our block memory address 132, and then we divide it by the number of lines in the cache, which is 100. So this is your small m, right? This is your small m. So the answer is 1 remainder of 32. This is what you remain with. Therefore, block 132 is going to be mapped at cache line 32. Okay, so to test this equation again, let's say we have block number 101. So this would be fairly easier to imagine. So to map it onto the cache line, we would divide it by 100 and the remainder would be 1. So the block 101 would be mapped onto cache line 1. So let's see if this table checks out. So I have block number 101, so that corresponds to m plus 1. Therefore, the cache line is going to be 1. Okay? So this effect, however, even though we mapped all these blocks onto the same line, for example, we have the 0m, 2m, etc. All these blocks are identified or distinguished from another using different tags. So note that no two blocks that map into the same line number have the same tag number. So we'll see what tag number is. So here we have a physical address. We can call this as the memory address or the physical address. So the physical address divides the memory address, or the physical address is split into tag, line, and word. Now this is just an example of the number of bits typically assigned to the tag, line, and word, but this is not always the case. So you would have problems in this chapter where you need to find out what is the number of bits for the tag, for the line, and also for the word. So we'll talk more on that later. Okay. So let's talk more on direct mapping. So direct mapping, we have seen this equation whereby this is cache line number equals to the main memory block address modulo number of lines in the cache. So consider cache memory is divided into n number of lines. We have seen that our cache lines was small m before. In this example, they call it n. Then block j of the main memory can map to line number j mod n only of the cache. So j mod n is j mod n, and you would get the cache line number. Okay, moving on. So this is direct mapping cache organization. So the time taken to find out whether the required word is present in the cache memory or not is called the hit latency. So in direct mapping, there is no need of replacement algorithm. This is because a main memory block can map only to a particular line of the cache. Thus, the new incoming block will always replace the existing block. So this is very important to take note. The new incoming block will always replace the existing block in that particular line. We have that system whereby a particular block already knows which cache line that it is going to map to. So there is no need for the replacement algorithm over here. So let's talk about this one, the direct mapping cache organization. So here you have your physical address or your memory address, and the tag and the line mix up for S. Therefore, your line would be R. If you would define your line to be R, therefore your tag would be S minus R. The tag plus line is equal to S. And then your word field, or typically they would also call this as a block offset, is denoted as W in this diagram. Okay, so let's imagine this scenario. We have our CPU. Our CPU wants to read a data or a memory from this memory address, or this physical address. So the first thing that the CPU would do is to actually ask its own registers, and if the memory is not there, it will go for the cache. So the memory address is brought over to the cache organization, and the first thing that the cache would do would to be look at the line field. The line field is, let's say the line field is 20, so it would go directly to line 20 over here, line 20, and then it would check for the tag. It would take the tags available in this cache line and compare it in the comparator with the tag that the CPU is actually asking for. If the tag is the same, which means that you would get a hit in the cache. So if it is not the same, if the tags are not the same, then you would have a miss in cache. So a miss in cache, the CPU would go for the memory in the main memory. So what are the advantages of doing this? If the memory is already in the cache, it means that you get the memory, you get the data that you want to read faster. If you would have to go access the main memory, we know that the main memory has a bigger capacity, which means that it is going to be, access time is going to be slower, and the capacity of the cache is smaller, but the access time is going to be considerably fast. So having the memory in the cache line helps to speed up the process of reading the data. And we don't want the CPU to access the main memory often, because the main memory is going to slow down our machine. Okay, so this is an example of direct mapping. So here we can see that, let's see. Okay, so our tag is 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bits over here, and our line plus word is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 bits for the line plus word, and we have 8 bits for the tag. So this is what it means over here. This is in binary. Okay, so let's talk about this. So this is the memory address. You have your line number. In this case, the line number is 0, and the word bits is 0, 0 over here. You have your tag, which is also a 0, 0 in hex. In binary, this is the representation. In the computer, it is interpreted as binary, so the hex is only for our convenience. Okay, so for this memory address, this is the data associated with this address. So let's say this is my house, and this is my address. So this is what it means: house, address, house, address, house content and address. So if I were to map this onto the cache line, I immediately know, oh, this for direct mapping for a line of 0, 0, I know that this should be at 0, 0 as well, cache line number 0, 0. So this is where it would be mapped at 0, 0, 0, and this is the data that is mapped from the memory to the cache line. And the tag is 0, 0 because this is the tag associated with this data. What about this data over here that I have highlighted before? So this data is associated with line 001, or just binary 1, right? And the tag number is 16. So on line number 0001, I can map this data from the main memory, and I put in the tag of 16. Now what about this line of data? This line belongs to 0CE7, which is basically this address over here. You can use a binary to hex converter to find out what this binary means in hex. So this corresponds to line number 0CE7, and the tag number is 16, and this is the data associated with this address. Now you can see that the tag numbers are different. They are not going to be the same, and it depends. So sometimes you can put in data 11111. It is still line number 000, but the tag would be different because it is a different data. Let's say this is 01, and the data is going to be 1, 2, 3, 4, 5, 6, 7. The line number can still be 000, but the data is going to be different because it has a different tag. Okay, same case over here. If I wanted to map, oh, we have a different line number 00 here. 0000, this is our field, and this is our tag. So see, it is not mapped onto this cache line, which means that if our CPU requests for this data that belongs onto this memory, that belongs to this address, which is line 0, tag 16, and it looks over to this cache, it's not going to be there. So you would have a cache hit. But if the CPU asks for line 000 with tag 00, then you would have this copy of data onto the cache, and you would get a cache hit. Oh, sorry, I previously said a cache hit, but it should be cache miss before. If the data is not there, you would get a cache miss. If the data is already copied in the cache, then you would get a cache hit. Okay, one more example of direct mapping. Let's see over here. We have, do we have a similar number? Okay, so we have a similar line number here. This guy and, oh, this is not similar. Okay, this is similar. So we have two line numbers over here, but the one that gets picked for the cache is with tag 16. The one that did not get picked for the cache is tag FF. So here you can see that it mapped this data 1, 2, 3, 4, 5, 6, 7, 8, because this is the line number that corresponds to that, and the tag is 16. It did not take this data, so if the CPU would request for line 3FFF with tag FF, then you would get a cache miss because this data is not copied onto the cache. Okay, I hope that makes sense. So to summarize the direct mapping, you have your address length as S plus W bits. So your S makes for the tag and the line, and this is your word field or your block offset. So S plus W is the total length of your memory address, and it is going to be in bits. So the number of addressable units is going to be 2 to the power of S plus W words or bytes. Let's say you have 32 bits of memory address, therefore your number of addressable units would be 2 to the power of 32 bytes. And then your block size is always going to be the same as line size, which is going to be 2 to the power of W. This is the word, and it is the block size or line size. We also call this as block or line offset. Okay, and then the number of blocks in the main memory is going to be 2 to the power of S plus W. This is your total memory divided by the block size. Total memory divided by the block size would give you the number of blocks in the main memory. And then your number of lines in the cache is M, or 2 to the R. This R, okay? So therefore, if you know how many bits your line is, let's say it is 8 bits, so your number of lines in the cache would be 2 to the 8. This is going to be M. So your size of tag is going to be S minus R. So what is the disadvantage of direct mapping? The disadvantage is that if a program happens to reference words repeatedly from two different blocks that map onto the same line, we have seen tag 16 versus tag FF. Tag 16 and tag FF maps onto the same line, which is, I don't remember which line. Let's just call it same line. That maps onto the same line. Then the blocks will continually swapped in the cache, because you are like having a cache miss. And then you would ask the memory, hey, please copy the data that I actually want, which is the data with tag FF into the cache. So the main memory would map this onto the cache, but the next time the CPU wants to read, maybe it doesn't want to read tag FF, but it wants to read tag 16. So now you are asking the main memory, hey, I don't want tag 16, I want tag FF. So the main memory is going to find the tag FF and map it onto the cache again. So you are like in this cycle over and over again. So this is what it means by continually swapped in the cache. And the hit ratio will be low because this is an issue. This is a phenomenon called as thrashing or conflict miss. So we have an example of direct mapping. I will go over this at the end, so stay tuned for this. Let's talk about fully associative cache. So fully associative cache is obviously the opposite of direct mapping. So it was originally proposed as an approach to reduce the conflict misses of direct mapped cache without affecting its fast access time. So remember that we had the conflict miss, right? Whereby we have two different tags mapped onto the same line, but sometimes the CPU wants a different tag and the cycle continues until the CPU asks for the same tag twice in a row. So to overcome the disadvantage of direct mapping by permitting each main memory block to be loaded onto any line of the cache that was free or available, hence the GIF over here. I am free from the direct mapping organization. So basically you have your block and you have your available cache. Some of the cache lines are already occupied with some data. Therefore, you would have these guys occupied. So the block that wants to map onto the cache line does not have to go for a specific line. It can go for any line that is available. In this case, we want to map block 1. Block 1 is free to go to any line that it wants. It doesn't have to follow the sequence that we have seen in direct mapping. So block memory can be associated to any cache line, hence the name fully associative. It doesn't have to follow a specific equation that we have seen earlier. However, the physical address split does not specify a line field number. Therefore, you fully depend on the tag. And if you depend on the tag, you would have to simultaneously compare all the tags in the cache to find out where the memory is located. Compared to direct mapping, of course, the fully associative cache avoids the conflict miss, right? It increases the cache hit. But because it has to compare all these tags at once, the latency also increases, which means that it takes more time to know if we get a cache hit or not. So there are pros and cons to this approach. Therefore, a replacement algorithm is required to suggest the block to be replaced if all the cache lines are occupied. We don't have the sequence mapping like the direct mapping. We don't have that equation going on. Therefore, we need some type of algorithm to suggest how to replace a certain cache line with new memory. So we will talk more on the different replacement algorithms later. So fully associative cache organization is as follows. We have the physical address or the memory address over here. It comprises of the tag, denoted as S, and we have the word field denoted as W. W is the same as before, but S was tag and line before for direct mapping. For fully associative, it's only the tag, because remember, fully associative does not have any line number. Okay, so the first thing that it would do is to compare the tags, right? So I would supply, the CPU asks, hey, I want to read this data at this memory address. Please find out if this data is at this, if this memory address is in the cache line or not. So I would pass over my tag to the comparator, and the comparator would take all the tags, each one of them in the cache, and compare it inside the comparator. It will compare all of this simultaneously, and then if there is a match, in the cache, then it would go for the word would be retrieved. If there is a miss, which means that the address that they want is not in the cache, the tag is not there. Oh, we have a miss in the cache. Let's go over to the main memory and retrieve the memory that we want. Okay, so this is an example of associative mapping example. Let's see how it does it. So same case, we have our main memory address in binary. This is our tag, and our word field is only 2 bits over here. Our tag bit is 22 bits, our word bit is 22 bits in this case. So this is the data associated with this tag memory. And this is the data associated with this tag. And this is the data associated with these tags. So let's see if we have any similar tags or not. Because in fully associative, all the tags should be different. So here we have tag 00, 0001. This is not the same. We don't have any same tags in our example. So that checks out. So no tags should be the same. And then this is from the main memory. We map it onto our cache. Our cache is smaller. This is why it's smaller over here. So you will see that the tag is placed at random. It doesn't even begin with 000. As you can see over here, the 000 is placed almost at the bottom of the cache. So again, it depends on where the cache line is free and available, and wherever it is available, the memory would map its data onto the available line. So here you would still have the number line for your cache. It's just that for the memory address, you don't have any field that specifies the line number. So the line number is picked at random, but you still have this numbering going on because this is part of the cache system. Okay, so example 4.2b, figure 4.12 shows our example using associative mapping. Yes, a main memory address consists of 22-bit tag and a 2-bit byte number. The 22-bit tag must be stored with the 32-bit block data for each line in the cache. So this is the data associated to the memory address. Note that it is the leftmost is over here, most significant 22 bits of the address that form the tag. So the leftmost 22 bits form the tag. Most significant 22 bits. Thus, the 24-bit hexadecimal address 16339C has the 22-bit tag 0586E7. So let's see how this is interpreted. So it says here that leftmost 22 bits is going to be interpreted like this. Leftmost 22 bits. So if you have a 00 going on here, you would have the 0 as your first bit, as your first digit in your hex. And then for the next part, oh, I can't see, 0 1 0 1 1 0 0 1 0 1. So 0 1 0 1, where is it? So it's 5. So this guy over here, for these two it's 0, and then for the next 4 it is 5. For the next 4, 1000 is going to be 8, right? So you get 0 5 8, and 1 1 0 0 is going to be C. Okay, C over here. And then for the next 4 bits is 1110, 1110. That's going to be an E that checks out. And the different bits are these guys over here. Oh, the last 4 bits. The last 4 bits. So here we have 0 1 1 0, which is a 6, right? This is a 6. This checks out. So you read it as such. Try for another address down here. So here we have a 3. So for a 3, this would be 0 0 1 1. Wouldn't it be? So I don't know what that is. So the 2 bit, oh sorry, we are looking at 2 bits, my bad. 2 bits, the first 2 bits or the leftmost 2 bits would be your number. So 11 is 3, obviously. Okay, so you have your 3, and then the next 4 bits is these 1111, which is, what is that? I don't see it here. I don't see it here. Is it not here? Well, it's supposed to be F anyway. Okay, and then you have another F. Next 4 bits, another F. And next 4 bits, another F. And the last 4 bits is 1101. 1101. Do you have it here? 1101. We don't have it here. But it is going to be a D. Because before F is a D, right? F is 111. So then the binary number before that is going to be 1110, which is a D. So 3FFFD. So this is how you read the address for your associative mapping example. Right. So to summarize associative mapping, note that no field in the address corresponds to the line number, so that the number of lines in the cache is not determined by the address format. So here you have your address length as S plus W bits. And then your number of addressable units would be 2 to the power of S plus W words or bytes. And your block size would be the same as line size. You would also call this as a block offset or line offset. And this would be 2 to the power of W. The number of blocks in the main memory would be the total size of your address divided by the total size of a block. So you would get 2 to the S. And then the number of lines in the cache, you will not know based on the memory address. And the size of tag is going to be S bits. So this is the field or the physical address split. It is split between a block number or a tag and block line or offset. So this is your W and this is going to be your S. S is your block number or tag. So now moving on. Oh, so we have an example. Of course, I will go over this at the end of the lecture. So now we talk about the last mapping for cache, which is the K-way set associative mapping. So the K-way set associative mapping basically combines the direct mapping with the fully associative mapping while trying to reduce the disadvantage of both mappings. So for direct mapping, we know that it is straightforward mapping and the retrieval is very easy, but it suffers a lot from conflict miss. However, in fully associative mapping, the disadvantage is increase the hit latency, the time it takes to determine whether we get a hit or a miss, due to the comparator having to simultaneously examine all tags. However, the advantage of fully associative mapping is the flexibility to place memory block into any cache line. So to overcome the increase in hit latency, we can counter this argument by saying that, oh, why don't we use a lot of comparators at the same time? So one comparator is dedicated to compare one tag with the memory address. But this would increase the cost of your mapping cache and also the complexity of your cache. So we don't really want this. So to reduce all these disadvantages, K-way set associative mapping was introduced. So set associative mapping, the cache lines are divided into a number of sets. So let's try to imagine that. So we have our cache lines. We have cache line 0 up until a number. Let's say our M is 100, which means that our cache line would go from 0 to a 99, right? So within these 100 lines would be divided into sets. So let's say each set has 2 lines. Let's say each set has 2 lines. Therefore, you would have 50 sets. So line 0 and 1 would correspond to set 0, and so on. And line 98 and 99 would be set 50. Okay, so a particular block of main memory can map to only one particular set of the cache. So the block, you have your block. Your block, it has been decided which set it can be mapped onto. Let's say block 0 can only be mapped onto set 0. Let's say, so block 0 can only be mapped onto set 0, but it has the freedom to choose either to map it onto line 0 or line 1, because you have these 2 options within set 0. So the direct mapping in set associative is that it has already been decided where the block is going to be mapped, which is block 0 is going to be mapped at set 0. So this is the direct mapping approach. But the fully associative approach is that even though it has already been decided, it can still have some flexibility in choosing which line it wants to go for. Okay, so this is the combination of the 2 mappings in set associative mapping. So each set contains k number of lines. So in this case, my one set has 2 lines, which means my k is going to be equal to 2. However, within that set, the memory block can map to any freely available cache line, hence the flexibility. So for example, we have 2 lines per set. We can call this as 2-way associative mapping. If there are 3 lines in a set, we will call this 3-way associative mapping. And if we have 50 lines per set, we would call this 50-way associative mapping. But typically, I think it is limited to 64, I think. Please correct me on that if you find other sources that prove otherwise. So a given block can be in one of 2 lines in only one set. So this is an example of set associative mapping. This is an example of 2-way set associative mapping. So here you have your set 0 comprised of line 0 and line 1, and they have their own tags. And then you have your set M, and then you have your line M plus 1, and you have your tags over here. I think this would be set M minus 1. No, this wouldn't be even set M minus 1, because this should be a different notation, set N, let's say. Okay, and then we have our main memory going from block 0, block 1 up until block J plus 2. Doesn't really matter here. So K2 suggests that each set contains 2 cache lines. Since cache contains 6 lines, In this example, we only have 6 lines. Therefore, we would have 6 divided by 2 lines per set divided by 6 lines divided by 2 lines. Oh, this is not a good way to write this. Divided by 2 lines per one set. Okay, so you would have 3 sets. So set 0 is set number 1. This would be set 1. And this would be set 2. If we are assuming the cache only has 6 lines. So this would be set number 2. Set number 1. 1, 2, 3. Oh, so we don't have enough lines here. Let's make 1, 3, 4, 5, 6. Okay. So block J of main memory, let's say they want to map block J over here, can map to set number J mod 3 only of the cache. We'll talk on the equation J mod 3. So it can only map at J mod number of sets in the cache 3. So let's say if block J is going to be equal to 20. Would that be an easy number? Let's use a smaller number. Let's say block J is going to be 7. This is block number 7. Okay. So block 7 mod 3, the remainder would be, I can divide this 2 times. So 3 times 2 is going to be 6. 7 minus 6, the remainder is going to be 1. Remainder is 1. So the cache number that this would be placed in is going to be at cache set number 1. Which is actually set 0. But they label this as 0. I don't think we should label it as set 0. Maybe set 1 and 2 and 3. So let's see if this checks out. So we know that we have our 1, 2, 3 and 4 line, 5, 6, and then we have our 7. So block number 7 is going to be mapped onto set number 1. But it can choose between line number 1 or line number 2. This would be block 7 can choose between line number 1 or line 0 or line 1. Okay. So this is how you use this equation. It is different than direct mapping. So you would have a cache set number here. In direct mapping, it was cache line number. And for this equation, it is main memory block address modulo or mod number of sets in the cache. But for direct mapping, it was main memory block address divided by the number of lines in the cache. So here set and set. For direct mapping, it will be line and line. Okay, so within that set, block J or block 7 can map to any cache line that is freely available at that moment. If all the cache lines are occupied, then one of the existing blocks will have to be replaced. Since we offer the flexibility in set associative mapping within a set, we would have to apply the replacement algorithm that we have briefly mentioned about in fully associative mapping. So this is K-way set associative cache organization. Let's look at it. So we have our memory address comprised of a tag, set, and word. So our tag and set would make up the S, denoted as S, and your set would be denoted as D. Your tag is S minus D. And then your word field is denoted as W. Your word field is going to be the block offset or line offset or the data associated to the memory address. Okay, so the first thing that this K-way set associative mapping would do is the set number field of the address provided by the CPU. The CPU is obviously requesting to read data from this memory address. It would first obviously check with its own registers. If it's not there, it will request it from the cache. And when it requests from the cache would look at the set field and look for its own set. So let's say the memory address specifies to look at set number 1. So here they would immediately go to set number 1, and within set number 1 we have 3 tags. So all these tags would be compared in the comparator to the tag that is requested by the CPU. So here, after they have compared, if the memory is within this set and tag, then it would be a hit in the cache and the data associated would be red. If it is a miss in cache, then it would retrieve the memory or the data from the main memory. Now, if you want to copy memory from the main memory, but the cache is full, a replacement is made in accordance with the employed replacement policy. Okay, so to summarize the set associative mapping, we have an address length of S plus W bits. The S is going to be comprised of the tag and also set field. The number of addressable units is 2 to the power of S plus W words or bytes. And the block size or line size or block and line offset is going to be 2 to the W words or bytes. And then the number of blocks in main memory would be the same as in direct mapping and fully associative. And then the number of lines in a set is denoted by K. The number of sets that you would have is going to be V equals to the 2 to the power of D. Total number of lines in cache is M. We have seen this in direct mapping, the total number of lines. But in this case, M is also equal to KV because K is the number of lines in a set and V is the number of sets that we have. And then for the total size in terms of bytes, this would be K times 2 to the power of D, which is the size of the cache in bytes. Then we have the size of the tag, which is S minus D bits. So let's talk about an example of two-way set associative mapping. Let's first interpret the tag hex over here. So here, our tag, we know that it is 9 bits. So if I were to divide this into 4 bits, I would have 1, 4, 4, right? So the first bit of my tag would be the first digit of my hex. And then the next 4 digits, the next 4 binary digits would correspond to the second digit of my hex. And the last 4 digits of my tag will correspond to the third digit of my hex. So let's see if this is actually true. So for the first one, we're looking at this one. This is a 0. And we can see that this is also a 0 for this one. And this is also a 0. So it checks out. And this is a 1 and a 1, a 1 and a 1. So the first bit here is the first bit of our binary tag address is our first bit hex address. And then the next 4 would be 0, 0, 0, which is a 0 over here. And still a 0, still a 0. We have a 0, 0, 1, 0, which corresponds to a 2. And then do we have others? We have a 1, 1, 1, 1, which corresponds to an F. And then for the third digit, the last 4 is a 0. It's a 0 over here. And then we have the last 4 digits, 1, 2, 3, 4, 1, 2, 3, 4. This should be a 1. Okay, I'm not sure about this one though. It's 9 bits, right? Okay, let's see the rest. We have, let's see. We still have F over here because it's basically still 1, 1, 1. Okay, so I'm not sure why this is not right. This is supposed to be 1 and 1. Okay. Let's see if the 1, 1, 0, 0 is actually C in our hex binary table. 1, 1, 1. So C is 1, 1, 0, 0. Okay. 1, 1, 0, 0 in binary is C. In hex is C. Is this it? No, it's this one. So 1 1 1 1 0 0 is C. Yeah, so this one is wrong. So this should be 0 0 1. Okay. And then we can see that for tag 0 0 0, it is mapped onto set 0 0 0. And then for set 0 0 0 1, the tag 0 to C is mapped onto here. And then for 0 0, we can see that the set number for the cache would be the same as the set number in the memory address. So here you have a set number of 0 0 0, and yes, it maps onto set number 0 0 0. For set 1, does it have 1 here? Yes, it does. This is set 0 0 0 1, and the set number is also 0 0 1. Now you can see that here in the cache we have two. We have two boxes instead of one. This is because it is a two-way set associative, which means that this is the first line, and then this is the second line of the same set. So you would have the same set but different tags because they correspond to different lines within the set. Okay, so I hope that makes sense to you. Now let's talk about varying associativity over cache size. So here in this graph, we are seeing the x-axis with cache size in bytes. So it goes from 1K, 2K, 4K up until 1 mega. And then we have a hit ratio. The hit ratio is, the maximum here is 1. And this is in ratios. So we are comparing between direct, 2-way, 4-way, 8-way, and also 16-way. And these are set associative. So we are comparing all these different set associative and also to the direct. So here for 1K, we can see that the 4, 8, and 16 have the same hit ratio, which means that after 4-way, it reaches a plateau. And the 2-way will have a lower hit ratio, and the direct mapping will have the lowest hit ratio. And this trend is quite true for most, where the direct mapping is the lowest when compared to other set associative. But for 1 mega, direct mapping is the same, achieves the same hit ratio with the set associative mapping. But you would see that this is a very, very big cache size, which is quite unlikely in near future. So this is a simulation. Alright, so if we are going to observe 64K, we would see that direct mapping has the lowest hit ratio, whereas 2, 4, 8, and 16 have the same hit ratio. So what can we conclude based on this graph? We can say that direct mapping has the lowest hit ratio as compared to all the other set associatives, and a higher way of set associative. Let's say you have a 16-way set associative, is going to have a higher hit ratio compared to a 2-way set associative. So a higher way set associative will have a higher hit ratio. But it becomes comparable when the cache size is bigger. Okay? So in my next part, which is part 3, we will talk about the replacement algorithms and also do some practice problems. I'll see you in the next part.